So today we want to extend the idea of a derivative to higher order derivatives. And so we've learned that the derivative of the function f, which we can denote f prime is one way, f prime of x, that it itself is a function. Right? It itself is a function, the output of which tells us the slope at x on the graph of the function f. Okay? Well, since the derivative is a function, it has a derivative of its own. Right? Every function has a derivative, or, well, every function we can define a derivative. And so how would we denote that? Well, the derivative of f prime would be f prime prime, or what we like to say f double prime. This is called the second derivative of the function f. The second derivative of the function f. Now, the Leibniz notation, let's recall that if y is equal to f of x, then the derivative f prime of x is the derivative with respect to x of y, or dy over dx, right? This is the Leibniz notation for the derivative of the function. Or sometimes we will call now this, in this context, the first derivative, right? So what would the second derivative of the function be? Well, that would be the derivative, right, of the first derivative, dy dx. So the notation is the derivative with respect to x, d over dx, of dy dx, right? Remember what dy dx really means. It means the derivative with respect to x of y. So it's kind of like taking the derivative with respect to x twice, or what we write d squared dx squared. Because dx is, again, considered one variable, or one expression, if you will. It's an infinitesimal change in x. So it's the whole thing squared. But this is the way it's normally written, or this way, d squared y dx squared. So this is kind of a little cumbersome, but this is the way the second derivative is written using Leibniz notation. We can similarly define even higher order derivatives, like the third derivative, y triple prime, f triple prime of x. That in Leibniz notation is this right here, d cubed y dx cubed. Similarly, the fourth derivative, right? Now, if we take higher and higher order derivatives, this tick mark or this prime notation gets a little bit tricky. I mean, if we took the 16th derivative, who'd want to sit there and count that we've got 16 prime marks? So when it gets that high, typically we will put in parentheses a subscript with a number. So if it's in parentheses, this means the fourth derivative. Okay? Without the parentheses, that would mean take f of x and then raise it to the fourth power. So we do need the parentheses around it when we're talking about the derivative. This is the fourth derivative, or corresponding in the Leibniz notation, there's the fourth derivative. And this process can continue, and sometimes we talk about the nth derivative, right, of the function y. So that would be denoted this way. Notice the parentheses have to be around it, otherwise it means y to the nth power. Here's the nth derivative with the function notation, and of course the Leibniz notation. So a couple things is, you might say, why do we do this? Why would we even talk about this? Certainly it's a mathy sort of idea, but there are some applications. Some of you are familiar with this, and we'll look at it soon in an application later in the course, and that is that the function f, if it represents the position of a particle undergoing linear motion, so the distance, for say, from a fixed point, then the derivative of that function, which we'll see represents the rate of change of the position with respect to time, is what we call the velocity of the function, or velocity rather of the particle, excuse me. And the second derivative is the rate of change of the velocity with respect to time, for instance, and then that is something we call the acceleration. The rate of change of velocity is acceleration. And so we can use these in real settings. Now, another area is, some of you will take Calculus 2 and differential equations, and there's something called a Taylor series, or what we call a power series representation of functions, and that's useful in a lot of contexts and some application. And in that context, we talk about this nth derivative, and so we'll need that for those areas as well. So we use this quite a bit in different contexts. This is a little bit mathy, but there are applications to it. But as far as doing this, the actual work, it's not that hard. We're just taking the derivative again, so to speak, maybe multiple times. Okay, so let's just do an example. Let's find the first, second, third, and nth derivatives of this function here, x times e to the x. Okay, so let's start with the first derivative, which is f prime of x. Now, how would I take the derivative of this function? What rule would I have to use? X times e to the x. I have to use the product rule. And we looked at the product rule in the last set of lectures. So here we take the derivative of the first function times the second plus the first function times the derivative of the second. So what's the derivative of x with respect to x? That's just 1. What's the derivative of e to the x? That's just e to the x. And so we get 1 times e to the x here, x times e to the x. There's our derivative. I'm going to go ahead and factor out that e to the x and write it that way. But there's our derivative, and it's in factored form. So that's the first derivative. Now, what about the second derivative? How do we do that? Well, second derivative is f double prime. How would I go about doing that? Well, I'm just going to take the derivative of this function now. Take the derivative of this function. Now, I have a sum of two things that I have to take the derivative of. I'm going to use this one here, not the factored form. I mean, here you're back to a product. Here, I don't, well, I do have a product rule here, but we're going to see something very useful here in a minute. The sum of two functions, the derivative is just the derivative of each individual one. So the first one, what's the derivative of e to the x? And that's just e to the x. And then the next one, what's the derivative of x times e to the x? That sounds familiar. Didn't we just find the derivative of x times e to the x? Yeah. What is the derivative of x times e to the x? Well, e to the x plus x e to the x. And so that's the derivative of x e to the x, is e to the x plus x e to the x. Okay? So the derivative of e to the x, e to the x, the derivative of x e to the x is this part. So I can combine these though together. E to the x plus e to the x is 2 e to the x plus x e to the x. And again, there's my derivative. I'm going to factor out the e to the x again because we're going to see a pattern here. This leaves 2 plus x. Let's see if we can see a pattern, because that's what we're going to need when we get to the nth derivative. Let's do the third derivative. All right, f triple prime. So the derivative of this is the derivative of each one of these added together. The derivative of 2 e to the x, 2 is a constant multiple, we can pull it out, times derivative of e to the x, which is e to the x. So it's just 2 times e to the x. Notice I don't need a product rule there because 2 is a constant function, right? Constant multiple really is what we're using, a constant multiple rule to go here. And then again, what's the derivative of x e to the x? Well, that goes back to the very first one. We know the derivative of x e to the x is right here, plus e to the x plus x e to the x. 2 e to the x plus e to the x is 3 e to the x. And I get e to the x times 3 plus x. Okay. Well, we could do the fourth derivative and fifth derivative and so on, but I think you're beginning to see a pattern. I mean, when I take the derivative of this to get the fourth derivative, I'll get 3 e to the x plus what? The derivative of this again was e to the x plus x e to the x. That's going to give me a 4 e to the x plus x e to the x. And you see how that's progressing. In fact, you can see it here, right? The next one, right? First derivative is this, second derivative this, third derivative this. What's the fourth derivative going to be? E to the x times what? 4 plus x. Fifth derivative would be e to the x times 5 plus x. And so on. So if that pattern continues, what is the nth derivative going to be, which is written this way? All right. First derivative, e to the x 1 plus x. Second derivative, e to the x 2 plus x. Third derivative, e to the x 3 plus x. So what's the pattern? E to the x n plus x. Right? Now, Not all functions exhibit such an easy behavior to see the pattern. This function x times e to the x does, and so it makes it easy to find the nth derivative. In general, it's a little bit challenging to get an expression for the nth derivative of a function, but it is a useful skill, as I said, especially if you go on to Calculus 2 and differential equations. Okay. Before we look at the next example, I want to talk about something called factorial notation. Okay, so we're going to do some more high-order derivatives, but for notation purposes, factorial notation is useful. Now, here's factorial notation. You see this exclamation point, so that doesn't mean we emphasize, we don't say 2 really loud here, but here's what we do. 0 factorial and 1 factorial both are defined to be 1. That may be a little disturbing, but that's has to be the case. We only define these factorials, we're only going to define them for whole numbers. Okay. There's another function called the gamma function that we can extend this idea to any real number. But here we do 1 factorial and 0 factorial is 1. 2 factorial, this is where it starts to make sense, hopefully, is 2 times 1, which of course 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1. You see the pattern? 5 factorial, 5 times 4 times 3 times 2 times 1. So it's just, in general, n factorial is the number n times all the whole number integer, positive integers that are less than it, right? All the way down to 3 times 2 times 1. So 7 factorial is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, these are the factorials, what they're called. And so factor, you can see we're turning into a product, right, which has factors. So maybe that's why we call it a factorial. And it's actually read 2 factorial, 3 factorial. So instead of the exclamation point, we just say factorial, 4 factorial. Note this, that 2 factorial is just 2 times 1 factorial. And 3 factorial, right, 3 factorial would just be 3 times, right, 2 factorial. And 4 factorial is 4 times 3 factorial, and so on. So we have these two relationships in general, which are very nice and helpful. Later on, say in Calculus 2, you'll use those a lot in something called the ratio test for determining the power series, convergence of a power series. So very useful notation. So I want to just introduce you to that if you've never seen that before. Some of you have. If not, it comes up from time to time. And it's helpful here when we're talking about, say, the nth derivative. We might need to use n factorial in the expression for the nth derivative. Okay. So with that, I'm going to use that somewhere in here, and we'll see where it comes about. Here's the function y equals x to the fifth. Let's just find the first 6 derivatives of that. So I'm going to use Leibniz notation this time. dy dx is the first derivative. Derivative of x to the fifth by the power rule is just what? 5x to the fourth. Just simple. Bring the 5 down, subtract 1. We know that that's a piece of cake. What's the second derivative? Well, that's d squared y dx squared. That's how we write second derivative in Leibniz notation. So this is going to be what? Bring the 4 down. And some of you say, well, 5 times 4 is 20x cubed. I'm going to write this as 5 times 4 and then x cubed, which, yes, is 20x cubed. That's the answer. But I want to, again, I'm going to be getting to a pattern here, so I want to leave it that as well. What's the third derivative here? Well, 5 times 4 is a constant multiple. Pull that out. Times the derivative of x cubed, that's power rule again. Bring down the 3x and subtract 1 squared, okay? Which of course is going to be 60x squared. But again, I like that pattern that we're developing here. The fourth derivative, all right, is going to be 5 times 4 times 3 times 2. Bring the 2 down, right? X to what? The first power, just x, which of course is 120x. Okay, fifth derivative. Well, fifth derivative is what? It's just 120 right? 120x derivative is just 120. This is a line of slope 120. But another way of writing 120 is what? 5 times 4 times 3 times 2. I can stick a 1 in there. It's what? 5 factorial. Okay, that is 120, by the way. But 5 factorial. What's the sixth derivative? What's this? A constant. What's the derivative of any constant? 0. Okay. We said just the first 6 derivatives. Could we take the 7th, 8th, 9th, and 10th derivatives and so on? Yeah. What are they all going to be equal to? 0. Right? The 7th derivative will be 0 because the derivative of 0 is 0, and so on. So from here on out, there's 0. So notice for polynomials, right, and this will be true for any polynomial function, each time we take a derivative, what? The degree of the polynomial goes down by 1. Right? And that will happen every time. The degree will go down by 1. But also, we see some patterns here, like if this is a 5th degree polynomial, right, what will the 5th derivative be, right? Well, it'll be a constant, okay? In this case, right, since it's 1x to the 5th, it's going to be 5 factorial. If there was a coefficient, say a, x to the 5th, it would be 5 factorial times that coefficient would be the 5th derivative. And then the 6th derivative is 0. So, could you then, based on this analysis, find the 99th derivative of x to the 99th power? That's what we're talking about here. That's what this means. What's the 99th derivative? Now, we're not asking you to go through the process of finding the 99, right, the first derivative, second derivative, third derivative, all the way to the 99th derivative. No. I'm expecting you to get that from this. What's that going to be? Well, this is very similar to x to the 5th. This is x to the 99th. The 5th derivative of x to the 5th was 5 factorial. So the 99th derivative of x to the 99th should be, I hope you see, 99 factorial. 99 factorial. Because each time I take the derivative, it goes down by 1 power. So the first derivative will be 99x to the 98th power. The third derivative will be something x to the 97th power, and so on, all the way down to the 99th, which would just be this constant, because the previous one will be 99 factorial times x, and its derivative is 99 factorial. By the way, 99 factorial, big number, really big. What's the 100th derivative of x to the 99th? Hope you see that will be 0. In fact, we can make a generalization then. What will the nth derivative be of x to the n? The nth derivative of x to the n. It's n factorial. And we see that when n is 5, we got 5 factorial. When n was 99, we got 99 factorial, and so on. And this says, what's the nth plus 1 derivative of x to the n? Answer there, 0, as we showed here and here. Okay. So again, pattern recognition helpful if we're talking about the nth derivative. Okay, so we'll stop here. In the next video, we will look at a couple more examples of just finding higher order derivatives in general. Good practice.